Well, I graded these, but Connor still has to take it, so you can't have them back yet. I'll give them back to you later. If you want to see it, you can. But. We gotta be here. He's on his way. He can come soon, fashionably with. No, it's not. But he does come. That's good. For all the exam was pretty tough. So. Scores weren't like stellar, but they were disasters overall, so that's good too. Kind of an average exam. So if you got like in the 80s or high, pretty good. Pretty good. All right. 3 minutes until we start. How's everybody hanging in there? We have a break coming up soon, don't we? Easter Sunday is almost here. When is this break? Let me look at it. Oh, congratulations on the. Hope the pressures of adulthood don't overwhelm you. Right. Yeah. I guess it's more in April. How am I doing on schedule here? I'm a little bit ahead. That's never really happened before. It's all right. Gives us more time to review things at the end of the semester. Did I turn this thing on? Did not. That's why I did not hear the sound of. All right, Abby. Better now. Yeah, I imagine. Says my default microphone is now this earpiece. That's what I want to see. Oh, net changes next. That's good. Getting there. I have to assign a project for you. I haven't posted it to Moodle yet. But I can. I haven't selected a due date. Let's talk about a project. So which one do I think I want project B. I'll send it to you. I like to do elaborate backstories to my projects. I have to update the date so that it's this spring semester instead. It's from one of my dear friends, Meryl Paskins, who runs a turtle sanctuary in the great state of Texas. And he specializes in the treatment of turtles that have been traumatized by nearly fatal traffic incidents. And she's just been informed that the county plans to build a major highway past her turtle sanctuary. And obviously that's going to stall the healing process. So there are 2 highway proposals. And basically for this project, what you'll need to do is figure out which highway proposal causes the least trauma to the already traumatized turtles. You may be wondering, why is this class all about turtles all of a sudden? I didn't see that one coming. Well, the year before you, they really liked turtles, and so I just made every problem about turtles, and they were just like, this is great, keep it up. I need more turtle-based problems. So there we go. I'll share this with you on Moodle. one thing to know about this project is you don't need to work alone. In fact, I highly encourage you to not work alone. You can you can work in pairs, or if you want to form a group of 3, you can do that as well. If you need help finding buddies, let me know. I know how to, introduce people. I'm great for networking. So basically what you'll have to do for this project is give a typed report. So it's an optimization problem, but you're going to have to give a typed report of your solution. And you may be thinking to yourself, how's that possible? There's so much math. How do I type it? Good news, you can type math in Microsoft Word or in Google Docs. They both do it. I've included links for resources on how to do that. Now, one of the things that may be a little disorienting at first is that the project has to be written entirely in paragraphs using complete sentences. You should be somewhat familiar with this concept from our WISUPs, right? In sentences using paragraph. You remember that, right? Yes, those were a series of warm-up exercises to get you ready for writing a project report. Basically, you will need to make sure that there will be variables in this problem that you get the freedom to define. You have to make sure you define them. If you have a diagram in mind, you should provide the diagram. You should make sure you make sure that you explain your steps. That includes explicitly referencing material in the problem statement. You're supposed to write in a way that guides the reader through the solution process. In general, you're supposed to write in a way that a classmate could understand, okay? And of course, you should have the right answer in the end. That's important too. So you will need to provide explicit computation of derivatives, but you are allowed to use a calculator or Desmos to find critical points when the algebra is just impossible. And for this problem, some of the algebra will be impossible. So that's fine. Right, yes. A little picture. Yeah, yeah. So basically I have three main components. One is the problem statement, which is basically a rewording of the problem in your own words. You'll notice that when I write my problem statement here, I include lots of information that is just irrelevant. Like, you don't need to know that I'm a generous donor to their program. That's not important. You don't need to point out that one of the shortcomings of becoming a turtle therapist is you don't need to learn calculus, and now Meryl Taskins really wish she did. You don't have to, basically restate it so that it doesn't have basically my my wild musings, okay? You can tell I get bored sometimes. I get bored. So that's what this first component is about. And then your solution is written for if you were, say, just a classmate. But then you need to provide a summary. And I accidentally clicked on things. And a summary is a little different. The summary is like your final answer. You don't have to explain how you solve the problem, but you need to communicate things to Meryl so that she can understand it, okay? She doesn't know calculus. So you need to state everything in plain English. And of course, if you do a fantastic job, you'll get extra credit. Last year, I assigned this on April 14th. That's when I assigned it to be due, but I imagine maybe a slightly different day would be better. Yeah, we're not going to make it due then. I'll update the due dates and I'll post this on Moodle, but I wanted to go over it now before I forgot. Okay. So there is that. And I keep having Notepad++ opening up by accident. All right, are there any questions before we get going today? I will not be in my office this afternoon in case you were really hoping to see me. I have to drive someone to the airport. I'll be here till maybe 3. So Jerry, you can try your luck. I may be here, I may not be. Okay. So let's go over what we had done last time because that was a while ago. That was essentially a week ago. We were learning something called the fundamental theorem of calculus. And the purpose of the fundamental theorem of calculus is basically to provide a really easy way to compute these quantities here that we call definite integrals. Definite integrals, as you may recall, represent the signed area between the plot of a function and some interval from A to B. And so the definite integral gives a concrete numerical value. And we have been estimating this quantity in various ways. First, we estimated it using right endpoint approximations. And then we discovered that if we let n go to infinity, the approximation was exact. So we learned how to actually compute these definite integrals that way. We also learned how to approximate them using Riemann sums, which are kind of a glorious generalization of the idea of right and left endpoint approximations. And what the fundamental theorem of calculus says, at least part 1, is that all of those very difficult computations we did, especially with the n going to infinity, there's a much easier way to do them. And that is to find the antiderivative of the function you're integrating here in the definite integral and evaluate the antiderivative at the endpoints of the interval. So here's an example that illustrates it. Let's say I wanted to find this definite integral here. This is essentially the area between the line y equals 4x and the interval from 2 to 4. One way I could compute this is, well, let my little f of x be 4x, and then take the antiderivative of 4x. We know that's 2x squared plus c. Though, as I mentioned earlier, when doing definite integrals, it's fine if you just pretend c is equal to 0. That works. You can't do that always when taking antiderivatives, especially if you have an indefinite integral. An indefinite integral is just like a definite integral, but there are no numbers. And so using the fundamental theorem of calculus part 1, we know that this definite integral here is just the antiderivative evaluated at 4 and 2, and you take the difference. And so you get 2 times 4 squared minus 2 times 2 squared. That's 32 minus 8, which is 24. Okay, that's the idea there. Now, later, down here, I wrote down the short way of writing that same problem. I moved it down here so you could have reference to it while you worked on some of these group work problems. The sort of more concise way of doing this type of problem is to look at the integral here, the 4x again, write down the antiderivative 2x squared, but then to draw this vertical line with a 4 and a 2 located there and there. And this basically means take the antiderivative and plug in x equals 4, plug in x equals 2, and subtract them. So the shorter solution is nice because you don't have to say what your little f of x is or what your big f of x is. It's just, all implicit. And so last class, I left you to work on some of these integrals. And so let's do maybe part A together just to refresh. We'll do it here. We have a definite integral. It's the integral of 3x squared from 0 to 3. First step, we got to find the antiderivative of x cubed. What's the, oh, dang it. All right, I accidentally gave it away. What's the antiderivative of 3x squared? X cubed. And then I draw this vertical line here, and that tells me we're going to plug in x equals 3, so we'll get a 3 cubed. minus is 0 cubed, and 3 cubed is 27. The answer is 27. That sure beats doing a right endpoint approximation, don't you think? That would take a lot longer. So continue on with these. Some of them are easy, some of them are hard, some of them are really, really tricky. But do the best you can. I'll walk about the room and see how everyone's progressing. Sound like a plan? All right, let's go then. Yeah, bring my drill here and fix this. What are you working on? Yeah, that's right. Good job. What are you working on, Megan? Part B. Very good. Okay. Hi, Liam. I'm just sort of pushing myself into everyone's business. Okay, good. That's correct. And how's it going, Liz? Yeah, yeah. This is kind of fun. When you first do these, they're not that bad. Here, I'm gonna get a fun book out of my office. I have to show you all this book later. Online students, you can always just unmute and say, is the answer to part something this? And I can say yes or no. You want to check your work or anything? How do they custom make that brace, Connor? Wow, it's very impressive. You know, in older times, they would have just stuck you in a cast, right? You were? Oh, wow. Okay. There was a string of my life where my arm was in a cast every summer for 3 years. Yeah, it was terrible. I didn't get a lot of swimming done. Let me put it that way. Ah, it sure is. If you don't like theta, you can make it an X instead, but it's a theta. How's it going, April? Wow, you got a lot done. Let's check them real quick. Yeah. What'd you get? 24. Yeah. And 2/3. Yeah. Oh, I have a negative there. I don't know why. What'd you get for the antiderivative? Ah, because when it's a negative there, right? then this will be a plus right there because it's minus a negative. Yeah. Oh, how's it going? Oh, very good. Except I believe it's actually a positive 127.5. It's the other way around.
Oh,
Yeah. And how's it going, Maxwell? Connor. Yeah, beautiful. So now you just need to plug in 2 and -2.
yes.
It's not fun. Yeah, that one's rough. To write that one down. So for part C, I don't know if I'm giving it away too soon here, but you should have this x to the 5th over 5 minus 3x squared over 2 or something like that. When you plug in for 2 and -2, you got to be really careful to include those parentheses or things will go very, very wrong. Parentheses are not optional. How'd it go? No, no, you're doing a different one. You're okay still. Too much conversation out there in the student area. Oh, Keelan, how's it going? Uh, well, you are correct that you did not do it right. The easier way to approach it is to write this as theta to the -3,
That's what I was thinking, but
and
then it
then
wouldn't be.
what you'll get is that because you add 1 to the exponent, if you add 1 to -3, you get theta to the -2. Then you gotta divide by that -2. So when you take the derivative of theta to the -2 over -2, you'll get theta to the -3. And basically replace x with theta here, but all right, there's this rule, and then there's this rule. And I'm using that one. Except my x is theta and my n is -3.
Yeah, I was thinking like the theta to the -3, but I was like, it's not.
No, 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 no.
But
Oh, yeah. Wow, look at that.
right for this, are we're adding 1 to this, right?
Yeah, I wrote down the integration law there. So yeah, it'll be a theta to the -2, and then it'll be over -2. What'd you get for part C? Hey, that's what I got. Oh, for B, part C, you just stopped.
Here in this one.
Oh, okay. Oh yeah, that's correct. Good job. How's it going, Joshua? Not sure. This is yeah, well, part C is a little off. I should point that out first. So what you have to do is you have to plug 2, +2 into both that and that,
Oh, okay.
and then plug -2 into both that and that. And as for this one, Yeah, you wanna write it as theta to the -3 d theta, and then do the integral.
I just. Don't you just like subtract?
Yeah, you have this theta that this is almost it, but you have to,
Okay, and then I do.
you'll have to divide that by a -2. And how's it going, Jack? You keep it as fractions. Good for you. That's what I do as well. But I also include the decimal. I do them both. Oh, I got oh no. 24. Yeah, that's the same. Well, it's positive 12.8. So I just have 64. Oh, I think this term should go. What happens here? Something isn't quite right. So 2. Oh, you got to plug +2, +2, -2, -2. I will write it up. Yeah. Yeah, part C is tricky. So you should have +2 plugged in. And then a -2 plugged in. And those parentheses are really important. How goes it?
I did not get.
Okay. Yeah.
Where is the positive?
I think if you're getting a negative, it's probably because you're plugging things in the wrong order. Yeah, these terms should be this term there, that term there. Yeah. Yeah. So you need to, you're taking the derivative here. So that you for this term. And this term actually just the antiderivative. So since it's a dy, the antiderivative of cosine y is literally just a sine y.
Okay.
Yeah. Hi, Zach. We're doing integrals. More of them. More integrals. Ah, it's amazing how Google Calculator can let you type that in so nice. They got correctly sized parentheses and everything. Wow, good for them. Part F and part G, I guess those are kind of mean. Part H is kind of mean too. I mean, once you get past part E, they're kind of mean problems. Try them out anyways. Close. So this one, it's actually, instead of a -4 there, you should have a -2. Because you add 1 to the exponent when you take an antiderivative. Yeah, I know, it's mean. How's it going, Jerry? You checking in with Lee every once in a while?
once in a while.
Every once in a while. Yeah, it's fun to work by yourself sometimes, I guess. You guys like it a lot. That's fine. That's fine. Online students, like I said, just I can hear you as I walk about the room. I have a little earpiece on. If you ever want to check your answer or yell at me for the problems being too hard, feel free to do so. That's always possible. Say, or if you're thinking, Brandon, the problems are too easy, I need harder problems. I can always make those up. That's not a problem. And now I'm always thinking Connor is raising his hand. Are you? No, no, you're just the brace is forcing it. Okay. That makes sense. it's kind of silly for me to try to fit all these solutions on one page, but I just try anyways. There we go. All right, D here. So if you're working on part D, I think probably the trickiest part is to recognize that 1 over theta cubed is the same as theta to the -3. And then the next tricky part is to figure out how to do the antiderivative of theta to the -3 correctly. You always add 1 to the exponent. So if I add 1 to -3, I get -2, and then you divide by whatever that exponent is. And then when I take the derivative of this term, I should get theta to the -3. I then want to plug in at 5 and 1. So I should get 5 to the -2 over -2 minus 1 to the -2 over -2. And I probably plug that in my calculator at some point. I'll get 0.48. Here, we'll do this one in blood red. What's the antiderivative of y to the 1/2? Yes. So Megan said you start with a y over 3 to the 2, right? And you divide by 3 to the 2, 3 over 2. And then what's the antiderivative of cosine of y? Sine y. And I put this in parentheses. I just have to plug in at 0 and pi. The other ones are harder. The entire b term.
Like if you plug B into
Oh, you're talking, oh, I see what I didn't know what b was at first, but now I do. Yeah, so if I do this correctly, I'll get a pi to the 3/2 over 3/2 plus sine of pi. Do you know what sine of pi is? It's 0. That's really convenient. Minus a 0 to the 3/2 over 3/2. Do you know what sine of 0 is? 0. Yeah, only that last term persists. So you got pi 3/2 over 3/2. Or if you want to write it like a normal human being, you'll write 2 pi over pi to the 3/2 over 3. There. That's the way we write it in civilized society. Yeah, you can also get it like that. Has anyone tried part F yet? Maybe. Let's discuss part F briefly. This one is really mean. Part F says, well, first find the antiderivative of sine. I gotta find the antiderivative of sine 2t plus pi. Well, first of all, what's the antiderivative of sine? Yeah, it's negative cosine. So we're gonna have this idea that there's gonna have to be a negative cosine of something. And what should go on the inside, you think? Yeah, the 2t plus pi. All right. So the question now is this in fact the antiderivative of that thing? No, Liz says no. Right, and we can check why here. If we were to say, take the derivative of negative cosine 2t plus pi. How would we take its derivative? Well, we'd have to use the chain rule, right? The derivative of negative cosine is sine. We keep the inside the same, and then what's the derivative of the inside? 2. So you can see we almost get sine of 2t plus pi, but we have a 2 showing up that we'd rather not be there. And so how do we fix this? Yeah, we'll divide by 2, yeah. Or I'll write it this way, -1/2 right there. And then we'll evaluate at pi over 2 and 0. I'll erase my scratch work here because I need all the space I can get. And so I'll have a -1/2 cosine. And if I plug in pi over 2, I will get a pi plus pi. And then I will have a minus this negative. And you know what a minus a negative gives you? A plus. Only in math can 2 wrongs make a right. Turns out this does not work elsewhere. 2 negatives do not make a positive. Somebody's like, something bad happened to me today. You can't make their day more positive by having another bad thing happen to them. That's not the way it works. Okay, and after we simplify this, we should actually just get -1. All right, let's do part G. I need another color. Green it is. Does anyone know what the antiderivative of secant tangent is? No, close. No, so close still. It's secant. So we'll plug in secant of 0 minus secant of -1. And if you're using a TI calculator at this point, you're panicking. Because if you look at your TI calculator, you will see that so many buttons are there. None of them are called secant. What did I just do here? I totally screwed up this screen. Windows, you were trying to be helpful, and now I'm just confused. Okay, hold on. Wait, we can fix this. There we go. All right, I was just trying to move the calculator. Here, make it as big as I can there. All right. Teaching another class there. Let's clear it so it's done. You can see you got sine, cosine, and tangent, but no secant. So how do you figure out, say, secant of 0? Well, this is where you have 2 options. And the easier of the options is to remember that secant of x is 1 over cosine x. Okay, that's the easier of your options. And so for this secant of 0, that's the same as 1 divided by cosine of 0, which is going to be 1. That's convenient. So that'll be 1. And then I got to figure out secant of -1. And it's going to be basically the same thing. Except it's a 1.85. So you get -0.85. Isn't that exciting? There we go. That's it. That's how you can do it. Now, if you're like, Brandon, I don't know about this. What happens if I forget this identity on an exam? Okay. I'm going to try to remember where this is. There's something called catalog. Trying to see if it's, I think it's under math. Yeah, no, not second. I think you just got to press math. No, it's not there. Somewhere. Table set, stat, calc, table, graph, plot. Oh, there it is. Do you see it right down there by zero? Catalog. It's not a catalog of all the different calculators you can buy from Texas Instruments. It's a catalog of all the functions that are available that are hiding that you cannot find. And so you could, if you were having a very slow day, just arrow down. It's a long way to secant. You'll notice that there's this A symbol up there. And if you look in green on my calculator, you can see there are letters for each one. I want secant. So if I press the LN button, there's an S there. It'll take me to all the function names that start with S. And I just got to find where secant is. Don't tell me it's not here. Oh, no, they don't even include secant here. Oh my goodness. I'm going and showing you all this. It doesn't matter. They're like, we're not gonna give a secant function no matter what. What you gonna do about it? I guess never mind. I thought this would work. Forget about that catalog, everyone. You just got to remember this identity. All right, H, did anyone figure out how you could do a problem like H? This one seems mean. How do you do a problem like H? And you gotta try to figure out some crazy function that when you take its derivative gives you this. Gives you a quotient, right? The problem with quotients is they're really hard to figure out, right? Like we've never discussed how do you figure out the quotient rule in reverse.
Could you
There's
like make it so it's like t plus 1 times 1 over the square root and then multiply it out and then do it like that?
Yeah, that's exactly what you do. Online student, by the way, for those of you who are concerned that I'm talking to the voices in my head again, this voice is real. I can't click elsewhere. It's OneNote is being really weird right now. Whatever, I'm gonna just write it, okay? It's acting dumb. All right, so here is part H. So the idea here, and this is a problem that I tripped up a few people on the exam, is you're going to sort of break it up like this. You can do that. I need a little bit more room for parentheses here. There we go, dt. 1 and a 27 there. And so what happens? Well, what does this thing simplify to? What's t over square root of t? It's gotta be something, right? Yeah, here, let's write it out. So this is t to the 1/2. And you could write that as t times t to the negative 1/2. And yeah, it'll be a t to the 1/2. Yeah. So we can write this as t to the 1/2. What about this 1 over t square root of t? What is that going to be? And that t to the negative 1/2. That's a funny looking t. I'm leaving it. There we go. I'm not going to do this problem. It's going to take too long. But we've set it up so that now you could do it. So sometimes you got to do a little bit of algebra massaging to get it in the form you can work with. Now, number 2, which is really kind of the last major problem. I haven't gone over how to do ones like this, but you can kind of get an idea of why this. Oh boy, OneNote's really angry at me, everyone. Hold on here. Let me close OneNote. It's just had it. It's just angry at me for taking pictures of things and moving stuff around. There we go. This one's interesting. It's interesting to plot it to see what it looks like, first of all, because this is a piecewise function. And I could hop on Desmos and do that, but I'm really not in the mood right now. I'm just gonna just plot it by hand. So it'll look, there's -1 and there's pi. And so the rule is use this function when x is less than or equal to 0. And so if I plug -1 into here, I get a +2. So my function will start there. And when I plug in 0, I get 1. So I am going to get that right there. And then the rest of it is going to look like this. All right. And so if you're asking yourself, what signed area am I attempting to find? It's going to be, when I do this definite integral, I'm kind of looking for this as my positive area there in yellow and my negative area there in blue. That's what that definite integral is going to give me. And so on one hand, you might think to yourself, oh, this isn't so bad. I just need to take the antiderivative and plug in at the endpoints, right? And so at first you may say to yourself, well, if I'm plugging in, say at -1, I should take the antiderivative of that, right? Oh yeah, you're right. That's exactly what I have to do, yes. Here we have a discontinuity. We have a jump discontinuity. If we look back at the fundamental theorem of calculus, we'll see that those aren't allowed. You're only allowed to use it on continuous functions. And so yes, Megan's right. We have to break it up into 2 integrals. She prevented me from doing it wrong on purpose. Good job. And when x is between -1 and 0, we can just replace the f of x with -x plus 1. And for x between 0 and pi, we can just replace the sine x here. And so the antiderivative of -x is -x²/2. The antiderivative of 1 is x. And I'll plug in at 0 and -1. And what's the antiderivative of sine? Yeah, negative cosine. And I'll plug in at pi and 0. And now I got to actually plug all this stuff in. So I'll have a -0²/2 plus 0 minus a -1²/2 plus -1. That's just for this first term. Hopefully you can follow all the steps I did there. And then I'll have a negative cosine of pi minus a negative cosine of 0. And that would be, when I compute it all out, the correct answer. So this first term goes away entirely, right? It's just a bunch of zeros. This one here, if we look at it, I'm going to have a -1², which is a +1. This will be a -1/2 and a -1, but it's got a, so it's actually just going to be 3 halves in the end right there. And that makes sense. If we look at the area under this curve, we'd be like, oh yeah, there's a 1x1 rectangle there and a half of it right there for that triangle. So yeah, that makes sense. And then for cosine of -pi, if we plug that in, we'll get a -1. So we'll actually get a 1 here. And then we have a minus a negative. Hold on, wait. Cosine of pi is, it is -1. Yeah. So I'll get a +1 there. And then I'll have a minus a negative plus a cosine of 0, which will be a +1. That's not really what I thought it would be. I've made a mistake somewhere, everybody. Does anyone see where my mistake is? No, it's a +3/2. I've screwed up somewhere. Cosine of pi. My brain keeps telling me it's -1. That makes sense to me. Cosine of 0. That's +1, -+1. Oh, it's because I drew the picture wrong. I drew the picture totally wrong. That's why. Oh man, see? You're gonna be like, Brandon, this is why we use Desmos. It's because you're not reliable. There we go. Okay, that's better. All right, yeah. Turns out the math was right. That's 7/2 right there. So that's how you do that integral right there. Now, I don't know if this is the sort of question that bothers you, that you stay up late at night wondering about. But when I was a student, I was like, okay, I know how to do the fundamental theorem of calculus. That's great. Why on earth does this thing work? Like, I know what antiderivatives are. Those are derivatives backwards. Got it. I know what the signed area under a curve is. Correct? Why on earth are they related to each other? And so like most people, I think when they encounter this sort of question, they're kind of like, well, look, obviously there wouldn't be this course called calculus if this wasn't true. And so you can kind of believe it because, society believes it. And so you're like, okay, I believe society. They can't all be crazy. But if you're like me, like when I was a kid, I can remember my family would go out to eat. I had 4 younger sisters. We'd go out to Chili's. And we always went into that thinking it was going to be a lot of fun. But it ended with kids screaming at each other. And then parents screaming at kids. It was always a disaster. But one of the cool things that I learned while at Chili's, my dad told me this because I was maybe getting a little out of hand. He was like, Brandon, let me tell you something about right triangles. This was him teaching me math. He was not a mathematician, by the way. He worked in construction. He was like, check out this right triangle. And he told me the Pythagorean theorem. He was like, this is true no matter what right triangle you look at. A squared plus B squared equals C squared. And I immediately thought, you're a liar. You liar, because I know for a fact that there are infinity triangles out there, and there's no way anyone could check them all to see if this equation was true. There's not enough time. I was very skeptical. I don't know if I communicated that to him, but I remember thinking, hold on, wait, how could anyone know something like that? And if you took a high school geometry course that did proofs, hopefully you came away with some idea on why it's true all the time for all triangles. But that kind of then leads you to also question, well, is there like a proof or a logical argument for why the fundamental theorem of calculus is true? And the answer to that is yes, and I will spend the last 10 minutes of our class giving you one. This will not be on the exam. This will not be on the homework. This is just for fun. And in order to understand why the fundamental theorem of calculus is true, we need to remember another theorem called the mean value theorem. We never proved this theorem, but we're going to pretend like we did. All right, so the mean value theorem, as you may recall, I had this picture for it. Here is my function. Here I'm calling it big F of X. There's a reason for that. Earlier it was called little f of x, but I'm calling it big F of X now. I have this function big F of X right there, and I have a value, let's call it A. Maybe A is here and B is here. Those are my A and B. And when I look at what A is, the point A on my curve and the point B here on my curve, I can connect them with this secant line here, this black line. The slope of that secant line is given by this equation. Remember the function is big F of X here. So it's big F of B minus big F of A over B minus A. And so the slope of that secant line right there is this quantity here. And what the mean value theorem says is that there's some special value C that when you look at the slope of the tangent line at that point, the slope of the tangent line is the exact same as the slope of that secant line. And in other words, you can find a tangent line that's parallel to your secant line through any 2 points. And so this is the mean value theorem, and it is technically kind of difficult to write a complete proof of it, but I think most people find that believable to some extent. So we're just going to believe it. And so let's now prove the fundamental theorem of calculus. Just to recap, fundamental theorem of calculus is this. Fundamental theorem of calculus part 1. There we go. So let's write a proof. Proof of this. We're going to use that mean value theorem. I don't do proofs much. I do more of them in Calc 2 at the very end, but this is the one time I do them in Calc 1. So the first question we have is, well, how do you prove what is a definite integral anyways? What is that? And basically the idea is the definite integral is what you get when you take Riemann sums and you let the widths of those subintervals go to 0. And so what we're going to begin by doing is we're going to consider a partition P. Let P be a partition of the interval from A to B. And so if you recall from when we were doing Riemann sums, we would write it like this, like your x naught would be whatever your A is, and then the next sort of division point would be x1 and x2 and so forth. And let's imagine we had n of these. Xn is the last one, and it equals b. That we're going to let that be a partition. And now what we're going to do is something kind of strange. We are going to consider a summation from out of nowhere. Consider this nice summation. This is the sum from 1 to n of f of x I minus f of x I minus 1. So we're going to consider the sum of big F of xi minus big F of xi sub I minus 1. And you might be saying to yourself, why would I think about that, Brandon? That seems silly. But trust me on this. Now, let's imagine we wanted to write out the first few terms. Well, when I equals 1, I would get f of x1 minus f of x0. That's my first term. That's when I equals 1. Then when I equals 2, I'll get f of x2 minus f of x1. So that's when I equals 2. When I equals 3, I'll get f of x3 minus f of x2. And obviously, I can't write out all the terms. The last term would be f of xn minus f of xn minus 1. There we go. And that's what it would look like. Now something kind of neat happens. Check out, I have an f of x1 here and a minus f of x1 there. So what happens? Well, I've got a plus and a minus of them, right? So these two terms cancel each other out. So does the x2 and that x2, they cancel each other out. And you could keep going, and this would cancel out with something in the dot dot dots, and this would cancel out with something in the dot dot dots. And in the end, what you would get is negative f of x0 plus f of xn. And f of x0, that's what we call A. And xn, that's what we call B. And you start to see something that looks kind of familiar. That's one side of the fundamental theorem of calculus. All right, now for the next part. So we have this partition here, And what we can do is we can choose sample points, as we called them. Remember, sample points are just points in between each of those division points. We choose sample points CI in these intervals. Here, I'll stick it like that. In this interval, such that, and I'm going to purposely choose my sample points so that f of xi minus f of xi minus 1 over xi minus xi minus 1 is equal to f prime of ci. So if you're trying to imagine this with me, what I'm doing is something like this. I have this function, f of x here, and I have a partition. I have maybe a is here and b is here, and maybe this is x1 and this is x2 and this is x3. What I'm doing is I'm looking at sort of these individual little subintervals, and in each of these subintervals, like let's say I focus on this one here, right there and right there. Well, that might not be the best one. Let's do this one and this one here. I can draw a tangent line just like that, right? I can draw tangent lines, I mean secant lines between any of these 2 points that make up this picture. And what I'm doing is I'm saying, okay, fine, you can draw those secant lines, but guess what? I can pick a point so that the tangent line is parallel to the secant line. And so my C1 is picked so that whatever the slope of that secant line is between those 2 points, the tangent line slope is going to be exactly the same. And so I could try to draw a better picture of that, but I'm out of time almost. Oh dear, I didn't mean to see that flash to 104. Now, another way to write down this equation is to say that f of xi minus f of xi minus 1 is equal to f prime of ci times xi minus xi minus 1. And we had some nice notation for this. Typically, when we take the derivative of big F, we denote that by little f. And this we denote by delta xi. And so what happens is that this weird sum I was considering earlier, this I equals 1 to n of big of f xi minus big F of xi minus 1, I can also write it as the sum of I equals 1 to n of f ci delta xi. And this is what we called a Riemann sum right there. And since we already know that this sum here, the sum of the f of xi minus f of xi minus 1 is equal to f of b minus f of a, then it follows that my Riemann sum, when I choose my sample points that special way, is always equal to f of b minus f of a. Isn't that amazing? So you pick a partition, you can always find sample points in that partition so that it's f of b minus f of a, and then all we have to do is take the norm of our partition to 0 to get that the definite integral of f of x dx from a to b is exactly this. So this is what we call a proof. They can be kind of hard to understand at first. If you ever want to learn more about them here at Houghton, we have a course called Intro to Proofs, but we don't prove things about calculus. Okay, there's a whole course called Real Analysis where people go over these proofs. It's a 300 level math course. And this is just sort of a side note for it. Okay, thanks for humoring me when I went over. Any questions, online students, before I hang up?
I'm aware that I'm probably not okay, I'm aware I'm probably not eligible for this, but can I please
You want to do intro to proofs?
no test correction.
Oh, test corrections? No, you're not eligible. But your test corrections are exceedingly simple. You can do them. I'm just not going to give you any points. Good job on almost a completely perfect exam. Yeah. All right. I'll see you later. Bye.